I want to continue to talk about things related to frost heave, but we're going to move to a different scale here. So these two individuals here are staring at the bottom of the Greenland ice sheet, and what they see is this massive material here that is frozen into the dirt, or the ice has picked up from the underlying dirt. And the question is, what did that? And so they're pondering this question. And I'm going to say that the answer is who knows, but I'll give you a couple of different mechanisms. So to begin with, last time on Monday, I talked only about this problem here, which is responsible for the ripples in this road in Norway. And today, I want to get into talking about things underneath glaciers. But before I get there, I want to say a few more words about the freezing in soil. And this is just to recap the main message from Monday. We have this nice schematic diagram of freezing in a soil. Ice lenses form somehow. Water gets drawn up towards the freezing front. In models of this behavior, we think about this region as being partially liquid saturated below the ice lenses. Here's a picture of an ice lens over here. And the ice takes some shape within the pore space, which is limited by curvature in these regions and pre-melted films in these regions here. And I took you through a description of the generalized Clapeyron equation where we had these pistons and various things. This is another way of looking at the same thing. We've got the Gibbs free energy per molecule plotted on this axis, the temperature on this axis. So the Gibbs free energy is enthalpy minus entropy times temperature. Enthalpy itself has pressure in it right here. And the normal phase diagram, we think about taking the free energy of ice following this line, the free energy of water following this line, and at equilibrium they're equal. And of course the entropy of ice is smaller than the specific entropy. It's smaller than the specific entropy of liquid, and that's why the slopes are different. And with normal pressure melting, if we increase the pressure in both of the phases, because the densities are different, we get a new intersection here, which for ice happens to be at a colder temperature by this amount, and for most other solids, as we heard about yesterday, it would be over on the other side. When we talk about pre-melting or curvature effects on melting, what we're thinking about is only raising the solid pressure and leaving the liquid pressure back on this solid line, and so we get a bigger temperature shift. So you can work this out for yourself. These are all just straight lines. The offsets are just pressure divided by density, or multiplied by specific volume. And it's a pretty simple exercise to work out what these temperature shifts have to be. So that's responsible for the liquid. The liquid can move, and as it migrates towards colder temperatures, it supplies ice lens growth. Now, one thing I didn't mention is, well, how do we get the first ice lens to form? So we have this schematic diagram of a frozen fringe. We have water being sucked up through the frozen fringe, and I told you about two models for growing new lenses once we already have a lens. One of them involves the rigid ice model, where we unload the sediment contacts at some location and a new ice lens forms in between. And that's the one I want to continue to focus on. Where we unload the sediment contacts, of course, depends upon how the water is flowing, because the water pressure distribution along the connected ice here is important for the force balance. If we're at the ground surface and we don't have any ice to begin with, then we have more this situation. There's no reason for water to be flowing if there's no ice lens to be supplied. So if we start off with a hydrostatic pressure gradient in the liquid phase through this partially frozen region, then the force balance changes. And in particular, all we really have, if I imagine I'm applying a load here, some effective stress at the surface, all we have to balance is regular buoyancy at some level, say Z here, so there's this distance times the density, the buoyancy of the bulk density minus the water pressure times gravity, plus what we started with, being equal to the thermodynamic buoyancy, which winds up taking this expression. So it depends upon temperature and the temperature gradient down here. So there will be times, depending on what we do with the loading conditions up at the surface, and what the constitutive behavior is that goes into this liquid saturation profile that is the constitutive behavior of the soils, there will be times when we can just freeze ice in the pore space and we never develop lenses. And then there will be other conditions in which we can develop lenses. And so we can put this onto a regime diagram, and this is an example here for a particular set of constitutive behavior. And what's plotted on this axis is a surface temperature. You imagine applying some constant surface temperature at the surface here. And often in these kinds of experiments, we have a load sitting on top. That could be a building, for example, or a road, or just a rock, or whatever the laboratory experimentalist has decided to do up here. And if we start off with no load, we would be on this point on the axis, and we made the surface temperature cold but not too cold, we could grow needle ice, and that's this regime in here. If we make it too cold, then the ice is going to invade the pore space too quickly, and we won't be able to form needle ice anymore. We'll be in this regime down here where the multiple lenses form. Alternatively, though, if we increase the load that we're applying right at the surface here, we can also go from a single ice lens, even at the same surface temperature, into a case where all we can do is freeze in the pore space. So nothing interesting happens. Ice forms still, because we're still pulling out heat, but there's no lenses. So I just wanted to introduce the idea that there is all this range of behavior that can take place. Also, we can have different conditions in which we can develop other regime diagrams, and this was for a case of the evolution of a system in which there is a pre-existing lens. We could think about that as being needle ice. Some people would like to make that a pingo, and today I'm going to talk a little bit more about if that existing ice is a glacier. So we have a mass of ice, it could be kilometers thick, sitting on the ground. And what happens? Well, the regime diagram, what's been plotted here is the results of a bunch of numerical simulations and then some theory to come up with the lines. But to make it simple, on this side we're freezing. Things have been appropriately scaled, so this is the velocity. So we're freezing up here. On this side we're melting. So this is determined by the heat flux conditions that are being imposed. If the load here is not too big, in particular if it's less than some characteristic value at which ice will first start to penetrate into the pore space beneath that growing, or beneath that either growing or shrinking ice lens, then we can just have a steady lens with no frozen fringe. The ice can't penetrate because the effective stress is not big enough for it to penetrate. Alternatively, if we're melting, we can always go to a case where there is a steady lens, but if this effective stress is too large, ice will be sitting inside the pore space underneath it. And that can be a happy steady state as well. If we're freezing, that's when all the interesting stuff happens. And in particular, if we're freezing at a high effective stress, we can develop periodic lenses, just like in the China silt example and in the Taber's experiment. But there is this little regime in here where we can either have a steady lens or periodic lenses, and it just depends on how we initiated the system. Okay, so this is just a characteristic of the problem. I'm going to just ask you to believe, at least it comes out of the mathematics, and it comes out of experiments. Now, there's a different way to look at this that's maybe instructive. What I've plotted here is the thickness of a frozen fringe, scaled appropriately, as a function of the effective stress, also scaled appropriately. Scaled actually in the same way here, so that if the effective stress were equal to this penetration thickness, we would have a value of 1 right here. And each of these curves is showing how the fringe thickness changes as a function of increasing effective stress, but at different rates of either melting for positive melt rates now in this case. So I guess I have this is backwards. I apologize. I just added this a minute ago, so this should be V less than 0 because we're melting. This is melt rate. And over here, this is a freezing case. And what you'll notice is that in the melting case, the curve goes like so. It's curved in this direction. And in particular, the higher the melt rate, this is the case, the dashed line is for neither melting nor freezing, so that would be along this axis. That the fringe is thicker if I'm melting faster. And the way to think about that is that at the top of the fringe, right underneath the ice lens, we have to expel water if we're melting, and the faster we're expelling water, the higher the water pressure right at that boundary has to be relative to hydrostatic. And effectively that means that we're going to be able to lift up a larger amount of material, and we'll have a thinner fringe. If we're freezing, we're going to get a thicker fringe, but there's this rollover of the curve, and at this maximum point here, that turns out to be the boundary between where you can have steady lenses and where you have to have periodic lenses. Steady lens cannot be maintained in this shaded region here. Okay? So that's sort of how the system works. And this is going to come up a little bit later on, but I wanted to show it earlier. All right, so we've got lenses, we've got freezing in the soils. There are lots of interesting problems that one can build on from here. Of course, thawing is one of them. Once you've frozen all this material, we tend to thaw the material from the surface of the Earth downwards in the springtime. And of course, things are changing all over the globe. This is the change in the annual number of unfrozen days over a 40-year period till quite recently. And you see that in the Arctic, we're having something like 30 or 40 days less of freezing conditions than used to take place. And people are interested in this for all kinds of reasons. There's landform modification that is taking place. There are developments of new little lakes, and material is slumping in this case here. Biology, habitat, and wildlife is all being affected. And so there's a whole vast field of people that pay attention to this for very good reasons. That's not me. Well, I mean, I guess eventually you run out of days. So places like this, they're basically at 0, right? So, but up here, yeah, you can, it's that's something for the climate modelers. If we look at what things are over that same roughly 40-year period, in terms of how many days do we currently have of freezing conditions, you see that here in Cargese, we have basically less than 30, so the reds are less than 30. These are all the zeros over here, in these places. And, of course, the amount of penetration of ice into the subsurfaces does depend on how cold it gets, and this gives you sort of a qualitative picture that in all these red places, the most we ever see is just a little bit of needle ice growth, which is kind of cool to see. It maybe disturbs the top layer of the soil a little bit, but it doesn't really do much, okay? In these more yellow regions and the light blues, we can start getting frost heave in those sorts of regions. Of course, it depends upon the distribution of time at different temperatures, and that's not reflected in this map. But these are the places where we get frost heave and where we have to worry about it getting very muddy in the springtime because of all that ice melting and having nowhere to go because the underlying substrate is still frozen, and so it's impermeable. But I wanted to draw your attention to these extremely blue regions. In particular, all of this blue stuff here, and there's a lot of blue stuff up here, those are places where it's basically frozen all the time. Except that this is showing satellite data of inferred freezing conditions. And what you're really seeing is these places are glaciated. And so they've got glaciers on top, and yeah, the glacial ice at the top is, of course, at 0 degrees or less, otherwise it wouldn't be there. But underneath that ice, it is often thawed. So a lot of glaciers have melted zones underneath. And in those places, we have ice-water sediment interactions. It's going to turn out that the effective stresses are modest. So in terms of our regime diagram, we're in a realm where we might have steady lens growth or steady lens melting, or we might have something else happening under there. And the question is, what does happen underneath the glaciers? Now, it might even be important. That would be a bonus. We do science often because we're interested in the problems. If they actually happen to be important as well, then that's sometimes a bonus. Maybe we shouldn't be celebrating the fact that this is taking place, but sea level is rising, and it seems to be rising faster. And much of that sea level rise is being supplied by melting ice. So in glaciology talks, this is always the elephant in the room. It's the increase in sea level over time. And the question is, these people must have been, this must be the wrong reference given the time frame here. Either that or else they're not just doing science, but they're speaking to something else, some other power. So I'm going to tell you a bit about glaciers, and I'm going to give you a quick primer in glaciology and just how these systems work. So basically there are two ways of moving ice in glaciers. You can deform the ice, so that's cartooned up here. It deforms at rates that are typically in the order of meters per year. Okay? And there's some uncertainty. The viscosity of the ice depends upon the temperature and also on LPO, that's lattice preferred orientation. The ice is an anisotropic material, and how the crystals are lined up winds up being important. Glaciologists basically know this and forget about it. And then if you get debris in here, that's going to affect the deformation as well. The important thing, though, is that it deforms pretty slowly, just a few meters a year. Where all the interesting stuff happens is with sliding. So ice is famously slippery for some reason that we're going to learn about in the next lecture, I hope. And glaciers don't slide very quickly on, in the speed skating world sort of type regimes, but they can slide up to several kilometers per year. And basically, they're not sliding like speed skaters because there's bumps in the way. And maybe that's important for the speed skaters too, we'll find out. A problem is that the water pressure underneath these glaciers is not very well known. And what exactly is happening at the bed, whether the bed is deforming underneath these glaciers or whether it's just sitting there as a static substrate, is also a question. So I'll show you what is known from satellite observations. We have a cartoon here. It's about a decade old right now, but this is essentially the pattern of flow underneath Antarctica these days. All of these purple regions are ice shelves. They're floating. But you can see the flow fields. We have this stuff is not floating, and you can see that it's organized into these features that we refer to as ice streams or outlet glaciers. And most of the ice that is leaving both Greenland and Antarctica is going through these fast-flowing features here. And they're flowing so quickly, there's no scale bar on here, but you'll see one in a minute. They're going at up to a few kilometers per year. You notice these sharp boundaries, actually, between the quickly flowing material and the non-flowing material. These are sliding. Also, one thing I didn't tell you, well, maybe I'll tell you in a minute. The simulations that people make of long-term glacier dynamics that's related to trying to predict how the sea level is going to change over time, they're fantastic pieces of research, but you should only believe them insofar as, you know, maybe over a few decades. You shouldn't take their predictions as gospel, because there's a lot of things that we don't know. The biggest uncertainties are, what are people going to do? So how much CO2 is going to go into the atmosphere over the next while, and how is that going to affect atmospheric dynamics, snowfall and melting and so forth. And then it turns out that the oceans are extremely important, just the way in which those ice shelves get broken up and you know, icebergs calve, and all of that sort of process is extremely complicated and not fully understood. Okay, so these three things are big, big uncertainties. However, there's also these uncertainties too. There's exactly how the ice couples to its bed, how that sliding works. There's some uncertainty about ice rheology. And then, of course, different numerical formulations come up with different results. And that's exemplified here in this completely unrealistic but somewhat instructive model intercomparison project called ABUMIP, which is kind of an awkward acronym. But what they've done here is they've taken a bunch of models and they asked the modelers to keep the climate the same, so don't change any of the climate forcing. And when the ice gets to the ocean, chop it off and get rid of it, so we don't have to worry about ice-ocean interactions changing between these different models. We don't need to worry about atmospheric forcing or human behavior changing between these models. The only thing that differentiates these models are their treatments of the ice bed coupling, the ice rheology, and their numerical techniques. And what you can see is that this is over a 500-year period. You don't want to be, you know, banking on any individual model prediction. They're all increasing you know, the ice delivery to the oceans. This is meters of sea level equivalent change over this 500-year time span. But the uncertainty in these models is coming from our uncertainty about these three components. And I want to focus on things related to this. Now, I should say that despite the fact that these models aren't agreeing with each other, if you are concerned about sea level rise during your own lifetime or your children's lifetime, these uncertainties are not what is the important thing. It's really this. Okay, so how do these models work? Well, the ice bed coupling's not super well grounded in physics, certainly not as much as you would like. This is an example of a map of something, this alpha parameter here, which is a slipperiness index. So we know that on the bottom, yeah. Yeah, so it's this parameter here. So what we have here is that in the ice sheet model, we need a boundary condition that's going to tell us how fast we slide at a given basal shear stress. And in the model that Mathieu Morliam made, this is an inversion that went into his model, he has imposed this relationship between sliding speed and shear stress of the bed. So if you apply a stronger shear resistance, you don't get to slide as quickly. Okay? The problem is that the physics, we would like to have this a physically informed model, but we're not there yet. And so to make the models work, to impose a boundary condition, what is done is you either look, there's two different sort of schools of thought on this, but they're basically amount to the same thing. You look at the surface velocities that we see today, like from that movie that I showed you, and you figure out what the basal shear stress is as well. And for the most part, that's an easy calculation. These ice sheets are huge. They're very large spatial scales here. And we think about them as being thick because they're 3 or 4 kilometers thick, but that thickness is very small in comparison to the distance over which velocities change, except in a few locations. So for the most part, since there's this big disparity between the length scale over which velocity change and the thickness of the ice, it's a pretty good approximation to just say that the driving stress, essentially the surface slope times the thickness, is equal to the basal shear stress. Okay, because they have to balance. Yeah. Yeah. Yeah, isostasy is important. So it does deform. So isostasy is the fact that you add more weight to the surface of the Earth, you depress the mantle underneath the crust. It sort of scooches out of the way. But it does that on a very, very long time scale. So isostasy is important if we change the mass of Antarctica, the underlying continental material will pop up over time. Like it is continuing to pop up in places like Norway today. Yeah, in parts of Canada. But that's not that's important. It does go into these models, but it's not important over human timescales. Okay. So what you do is you look at current velocities, you infer current shear stresses, and you do a division, and you come up with a slipperiness index. Or you look at elevation and you do some modeling and you again come up with the slipperiness index. But the point is that slipperiness seems to vary an awful lot. And all the fast flowing places are super slippery, and all the slow flowing places are super sticky. And that's just a factor that, well, if they're flowing fast, and the only way we can make this relationship work is to adjust alpha. So that's how it's done. So effectively, when we model things going forward, we can change the climate, we can change the amount of snowfall and the amount of melting and so forth. But we're really just extrapolating from current conditions because there's no physics allowing us to change alpha. Okay, the bed is not being described. It's just only being parameterized. Now there are issues with this. There are things like these ice streams. This is another color map of speed going up to 1 kilometer per year here, down to basically nothing down there. And these are ice streams, these places here. There used to be an ice stream here. This used to be that color about 150 years ago. And this is a radar map. So we're looking at depth going down to the bed here. So they're using radar to infer properties of the ice. And what you might be able to see is that there are all these faint little layers in here, and those have to do with those volcanic eruptions that gave rise to those sulfate peaks that Gray showed. So it's just a change in dielectric properties that is reflecting a little bit of the electromagnetic radiation. That's what you pick up. And over here, there's nothing much of that going on because that used to be an ice stream, and all that ice got jumbled up in this marginal region. And so there's this nice line, which is where that boundary of the shear margin used to be. And over here, in this shear margin, or in the ice stream side of things, the reason that these things are able to flow so quickly and they have such sharp boundaries is that the bed underneath the ice streams is actually not strong enough to resist the driving stress. whereas has to be stronger than strong enough on the margins because they're actually holding things back a little bit, and that's not in the inversions for the slipperiness. So the models would need to refine their grids so much along these edges here that they can't. It turns out that you need resolutions on the meter scale to get the thermal regime right in this ice in order to get the viscosity right. And instead, we just alias all of this internal behavior into slipperiness changing across this boundary. So that's a problem. That's not the main problem I want to talk about today, though. It's just to let you know that there are interesting fluid mechanical problems that are in this field that remain to be solved. One thing we do have is we do have a lot of observations, and we're in an age where those observations wind up being saved to data repositories, and people like me that never collect the data get to benefit from everybody else's hard work. And this is an example. This is another ice sheet model. It's showing speed here. It's the same basic idea. Speed going up to a few kilometers per year and down to less than a few meters per year over the entire continent, and you can go and download that data. And I've said that, I have not said this. Much of the bed, it turns out, is at the melting point. So that means it can slide. And over areas that are roughly, take the thickness and square it over that kind of a footprint area, we can say that the basal shear stress, the average over a few kilometers, must match the gravitational driving stress because of the disparity between the length scales. And so we can estimate this basal stress because we know the ice thickness. That data is available. We know how the surface slope varies. And so this is the driving stress. And it's mapped down here using bed data from some particular freely available data set. And what you'll notice is that here the ice speeds are varying over many orders of magnitude, but the driving stress isn't really changing much. The map is mostly quite blue, and the places where it's yellow and getting into the warm colors up here, those are the places where we trust it the least because those are kind of mountainous regions, and the bed data or the thickness data is slightly off, and we could probably do a better job. But the main point is that it's mostly blue, and if I contour up the cumulative distribution of the driving stress as a function of how much is weaker than that driving stress, I get this black line for Antarctica. I get this green line for Greenland, obviously. And the blue line is just a poorer estimate for mountain glaciers, a compilation of I can't remember how many mountain glaciers. And the main feature that I wanted to draw your attention to is that, well, this is the 50th percentile here. This is the median of those driving stresses, and they're all about the same. They're all less than 1 atmosphere of driving stress. So they're all, the driving stress is in that same sort of realm, and by extension, the basal shear stress is in the same sort of realm as we're used to thinking about applied effective stresses for frost heave and processes like that. Do I want to say anything else about that? Oh, I did want to say that ice speed and driving stress are not spatially correlated, and I will try to convince you of that right there. So this is for Antarctica. This is all of the data points on 1 kilometer square grids covering the continent. The median condition happens to be right there. And I think we can agree that that does not look like something that we would want to say that there was a direct relationship between these two parameters necessarily. Okay, so what can we say about sliding from experiments? Now, I should say that this sounds bad. This, it sounds like I'm suggesting that the correlating velocity, sliding velocity, and basal shear stress and making the slipperiness parameter is a stupid thing to do. I don't think it's a stupid thing to do. It's the obvious thing to do. It's the right thing to do. It's just not got the physics that we wish that it had, because then we could evolve it as the system changed. And the reason it doesn't have the physics is that we can't really observe the local shear stress underneath the glaciers very well. And so we can turn to experiments to try to inform us about how everything works, though. And this is Neil Iverson is at Iowa State University. Luke Zoot is at University of Wisconsin-Madison. And the two of them have a couple of apparatuses, and I'll show you Luke's a little bit later. But they basically have an ice ring that they slide in the lab, and they slide it over beds of their own choosing. And they did a couple of neat experiments together. This one here is a sinusoidal bed. It's made out of a kind of a plastic, so it can't be deformed by their experimental conditions. And they're plotting the shear stress as a function of the sliding rate here, and these are, fast sliding rates for glaciers, but they're within the realm that takes place. And what they see is that at low sliding velocities, down over here, there is a direct relationship between sliding velocity and shear stress. And so this is what goes into the models, and this is indeed a direct relationship that they observe. However, it doesn't continue. And at higher sliding velocities, they measure the torque that is needed to twist their apparatus becomes lower. And the explanation is sort of shown in the cartoon. What happens is that as the ice is slipping over this bump, and this is vertically exaggerated, it's not quite so extreme as this, but as it's sliding over, the ice is trying to, it would like to stay on its bed, as much as ice wants to do anything, but it takes some time for it to creep. And it's sliding too fast for it to creep and maintain contact with its bed, and so a water pocket opens up, and they call these cavities in the literature. And the cavity, as you slide faster, it gets bigger, and these little stars are showing the shape of the cavity as they're sliding faster and faster. And once the cavity gets to be big enough, the extra shear stress that is required to slide faster over here and deform the ice over the next bump is counterbalanced by the fact that you're actually contacting less of the next bump. And so you go from what we would say is a velocity strengthening case over here to a velocity weakening case over here. So that's what happens with the solid bumps, the rock bumps, if you like. So some of glacier beds, we call them hard beds if they're made out of rock, meaning that they can't deform. We call them soft beds if they're made out of sediments, meaning that they can deform. And with the experiments over the sediments, they have something that's slightly different, but qualitatively in many ways is the same. They have an increasing shear stress with sliding speed, but it plateaus at some level. And the cartoon version of this is shown here. The idea is that the ice has to deform to get over bumps if you're sliding slowly. We call that form drag. But if you slide fast enough, you actually just pick up the rocks and you plow them through the sediments, and there's Coulomb friction, and that explains this rollover here. Okay, so that's the from the laboratory view of how sliding works under glaciers. Now the problem is that both of these sets of behaviors depend on what the water pressure is. Because the water pressure being higher would tend to make this pocket larger to begin with. And because the water pressure being higher would tend to reduce the effective stress and cause these curves to go downwards. Okay? They also depend upon, just exactly what does the ice do to the dirt. Does Does it infiltrate the dirt or not infiltrate the dirt? Because that's going to help to determine what that interface looks like. So we have to talk about water pressure, and this brings up a whole other class of models in the field of trying to predict what the water pressure is underneath glaciers. And at current times, these models of how the ice moves and how the water moves are usually decoupled. I think we're getting to a stage now where people that model the water transport underneath glaciers, which determines this liquid pressure, are being able to couple their models to the ice flow models so that you can have the coupled system going forward. That's the dream. But we do understand many of the basic processes. There's some effective normal stress that is applied to the bed. There's the weight of the ice. And the water at the base flows through rivers, and it flows through cavities. And the rivers are sort of shown here, and the cavities are shown here, just for schematic illustration. And the way that the rivers work is that the water flows through these rivers. They're called R channels. There's other kinds of channels too, but they flow through these rivers. The ice is always trying to creep shut and snap these things closed, but there's enough turbulent energy being dissipated that they melt back as well. And so you can have a balance where you maintain your river by this mechanism of creep closure and melting back. The cavities are kept open not so much by any turbulence in the liquid here, but instead just they're kept open by the fact that there's topography on the bed and you slide fast and you open up a cavity. And it's also trying to creep closed. Okay? Now, the rate at which things creep closed depends upon this parameter here. In glaciology, we refer to this in glaciology as the effective stress, which is not super helpful because we also need to refer to something else as the effective stress down here. So the mechanics of how things creep close depend sort of on the far field stress in the ice, the difference between that and the liquid pressure. And of course, along the conduit, so any place where you have a macroscopic amount of water that's up against ice, the water pressure and the ice pressure right at that location, the ice normal stress, they have to be balanced. Okay? So locally, the normal stress in the ice and the liquid pressure are equaling each other in these locations. And this is what an engineer would call the effective stress. So glaciology effective stress and engineering effective stress are not the same thing. And so we have different symbols for them, but unfortunately the same words. This creates all kinds of confusion in the literature, as you can imagine. And in particular, away from the conduits, the coupling between the ice and the bed, if we have Coulomb friction, that depends upon this effective stress. But the drainage networks depend upon how these things are creeping closed. So it depends upon this effective stress. The distinction is not often made in papers. Yeah. These rivers and so forth. So the puddles, I'll show you an image later of the numerical calculations, but the cavities on the other sides of obstacles depends upon the topography of the bed. And so if you have roughness elements that are meter square scale, you would expect the cavities to be meter scale. The rivers are typically, you can see these in, sometimes they're remnants and sediments, and actually eskers, eskers, they're these geomorphological features of boulders that are sort of the casts of dying rivers at the ends of glaciation. You can see them all over Canada and the northern US. And they're typically, again, sort of, kind of smaller than this room in size, but maybe half the size of this room, kind of thing in terms of diameter. that kind of scale. They are under megapascals pressure, but they're very, yeah. The difference between the water pressure and the ice normal stress or the effective normal stress can be megapascals. It can be megapascals, but it's often actually only kilopascals or hundreds of kilopascals. So there's an enormous variation. All right. Return you to thermodynamics once more, just to highlight another one of Dominic's papers. So this is actually Rob Stile was the lead author on this. I just wanted to emphasize this difference in melting behavior if you have ice inside a closed cavity or water inside a closed, this was a wine bottle for the French, but it's a beer bottle for the Canadian. And actually, I guess that's an Indian beer, so who knows. But in this configuration, the Clapeyron equation can be written out. The equilibrium temperature related to some reference melting temperature. If we're in bulk equilibrium, the normal stress in the ice and the liquid pressure are the same, and we get this dashed line here. And just for interest's sake, if you wanted to worry about the next order corrections and so forth, this is all plotted as a function of temperature, and this is the difference in pressure. They do start to become important at large stresses. The other circumstance that I've been focusing on is with pre-melting, or it could be with curvature effects. There's a difference between the normal stress in the ice and the water pressure in some reservoir out here, so that we can define the engineering effective stress in this way, compressive effective stress. And we get this version of the Clapeyron equation, which importantly has a much shallower slope on this type of a plot than this slope here. And again, the second order theory is down there. But so main point is that the effective stress in what we'll say is an open system, an open pore, can get up to substantial values at cold temperatures, but nothing like what broke this bottle over here. There's a detail, in terms of how this matters. We think about lots of different slotting processes. One of the slotting processes that's supposed to be important at very, very low obstacle size is this process of regulation, and this is a nice experiment that was done in the 70s, and it's been done since the 19th century by other people. Having a weighted wire pulled through an ice block and measuring the speed of that and what controls it and so forth. If this is done at room temperature, so the ice block is basically at 0 degrees Celsius, then the governing melting temperature difference across that obstacle is due to just bulk melting. If we're at a glacier base, if this is a solid rock and the only way for water to get from this downstream refreezing side to the upstream melting side is through this thin film, then it can be exactly like this room temperature experiment done in the 70s. But if we have a case where the ice pressure is allowed to change differently from how the water pressure changes across here, so for example, if this were a porous medium and the water was able to squirt through the porous medium much more easily than just through this little film here, then we could imagine that the water pressure on both sides of this obstacle could be almost the same. There could be almost no water pressure jump, but there still is an ice pressure jump going from upstream to downstream. And we can do a scaling argument for how fast we can move the ice from this side to that side for a given driving stress. And thermal conduction is going to limit it. So there's the amount of latent heat that's being released as we move from here to here. Here's the thermal conductivity, is that parameter there, the temperature difference across here, and the wavelength of this obstacle. And when you write in delta T using the generalized Clapeyron equation, allowing there to be differences in these two pressure jumps, you find that the bulk melting case goes about 12 times slower than the case where you have pre-melting. So it can be a significant effect. The question is it important underneath glaciers? And we have a problem, as I said, that in glaciology, the effective stress is a kind of a questionable creature. It has two different definitions, and you can, I'm going to say right off the bat, that you can make a model of glacier dynamics in which the engineering effective stress is zero everywhere. We know that the engineering effective stress has to be zero in places like this, where the water pressure and the ice pressure have to equal each other because there's no interaction with the bed. It's too far away. The question is, could it also be zero everywhere else? And I will tell you that I don't think so. And I'm going to show you a bunch of lines of evidence that I think point to it not being zero everywhere else. But none of them are incontrovertible. I think you could explain all of them away if you were to be a real pedant about it. So what are these lines of evidence? So, and also you were asking, someone was asking about the sizes of cavities. Here's an example where somebody did a nice numerical experiment. They went to a whole bunch of deglaciated regions and measured the bed topography and said, what would happen if we put a glacier on top of this bed and we slid it at some particular rate? How would we balance the driving stress and the basal shear stress? How would things be organized? And so this is an image of the normal stress on the bed over a bed that's formed in this way. You'll notice that the dimensions are tiny. So a lot of work going into the numerics on this problem. But the cavities are everywhere that's the dark blue, this level, because that was the applied water pressure, which was assumed to be equal everywhere along here. And there are regions where the ice is contacting the bed, and that has to support all of the weight of the ice above and all of the basal shear resistance as well. And we wind up with enormous gradients in stress along this hard bed, and that is perfectly fine for allowing water pressure to equal ice pressure, just as long as the film thickness that separates the two things is thin enough. Okay? So this is not going to be enough to make us know which situation is correct. The problem is that in glaciology, we can measure the ice thickness, we can measure the water pressure by drilling a hole and putting a piezometer down there, but we can't measure the ice normal stress at a particular location. We only know it averaged over a large area. Okay. So, I said that I think that the engineering effective stress is non-zero in some places, and here's my evidence. Lovely set of data. It looks very complicated. This is shear wave anisotropy data. We don't need to know what that means, except that it, well, we do need to know what it means. It means that it's the difference between a certain variety of seismic wave traveling in one direction versus having polarization that's going in a different direction. And there's lots of different sources of anisotropy, but you see that the dots here are color-coded, and the seismologists have become very, very clever at figuring out families of little earthquakes that tell them that each of these little dots is thought to represent a rock that a glacier has picked up, rubbing against a similar area of rock, so that the seismic wave ray path from the source to their receiver is basically the same all of this time. So this is one set of patches that is making earthquakes, this is another set of patches that's making earthquakes, and this is another one. And this is a 2-week period in the wintertime on Rhone Glacier in Switzerland. And what they would say is that the anisotropy that they're measuring along the flow path is the same for each of these 3 families of earthquakes in the wintertime, no matter when you're looking. Basically looks the same. The other line that's plotted up here is the river discharge coming out of Rhone Glacier. And you notice that the dimensions here, it's 0.3 cubic meters per second, 0.2 cubic meters per second. So it's sort of relatively slow river discharge. Because it's the winter time and everything's falling as snow, there's not really much water coming out. Same place in the summertime, and you can see that now there's different families. And the point is that the anisotropy is kind of being kicked off at just certain times of the day, and it seems to be following the same sort of cycles as the water pressure or the water discharge at the outlet river. And so they interpret this as suggesting that the source of the anisotropy that they're seeing in the seismic waves is cracks in the ice that are opening and closing in response to water flow rate changes. Well, the cracks can only open and close if the liquid pressure is more than the minimum compressive stress. The stress field will be anisotropic and so forth. But it suggests that the water pressure is probably less than the normal stress at the bed in those locations, because we would expect the normal stress to be the maximum compressive stress. Not definitive, but it's a suggestion, okay? There's certainly a difference between summer and winter, and we don't have a better explanation. Maybe a little bit closer to being definitive is this record. It's a remarkable record of temperature in Greenland. And what they've done is they drilled holes to the bed of the Greenland ice sheet, a number of them. These letters, I guess, represent them. And then the holes gradually creep shut, but they maintain a wire connection to the surface, and they're measuring the temperature at each of these little locations along here. And this is one snapshot in time showing those temperature profiles, but they actually collected these temperatures for a long period of time, for up to a couple of years in some cases. I mean, eventually the instrumentation breaks down and the records die. But this is a blow-up of the bottom region. And importantly, measuring temperature to the accuracy that we would like to be able to do in order to distinguish differences in pressure or differences in pressure and normal stress that control the melting temperature, it's really hard. But here, when the hole finally closed off, they have a measure of the local melting temperature at the in situ bulk melting conditions. And we'll call that T0 at the bulk melting temperature at the time that those holes closed off. The bottom instruments here are all above the bed at different elevations, ranging up to maybe 10 meters or so. And I've just taken that data, the last couple of points, and extrapolated down to what is the condition actually at the ice bed interface, and plotted that through time in these plots here. And then I took the medians. So each of these different colors is a different hole. There's the median bed temperature that I'm inferring along here. If the system were closed in the sense that it was only bulk melting that was taking place, I could calculate how the difference between the normal stress and the water pressure at the time that the hole closed is varying, and I get these numbers. So essentially, this would be, based off the Clapeyron slope for bulk melting, what the normal stress at the bed would have had to have done to maintain these cold temperatures down here, going down to 0.4 degrees below Celsius. And they would have had to stay at levels of several megapascals of effective stress, if you like, for periods of, up to a couple of years. And if you had little flaws in the ice, we would expect to again open up cracks, if that was the case. So I would propose that it's difficult to have these kinds of normal stresses and not break the ice and have the water squirt out somewhere else. Alternatively, if this was pre-melting happening down there, then these are the effective stresses that one would expect if the ice normal stress were different from the water pressure and the ice in the bed were able to interact with each other. And those are more in the 100 kPa sort of range, and that's sort of normal. So again, not definitive evidence, but it's suggestive. This one I'm not going to take the time to go through, well, maybe I will a little bit. We do have data for melt rates underneath Greenland. And we could ask the question, we know that the drainage systems are kind of complicated, but we know that there must be rivers or other sorts of conduits. And there's regions in between them where the ice is in close contact with the bed. And we could ask for a melt rate that we can get out of this data, what would the transmissivity, what would the flow characteristics of the porous medium underneath this ice need to be in order to allow the water pressure and the ice pressure to be the same? So in other words, I would need to make it really, really hard for the water to squirt out somewhere else in order to allow the water and the ice pressure to stay equal to each other. Otherwise, the water is just going to squirt away and we'll have a difference. Unfortunately, I don't know the sizes of these areas. I don't know the volume fraction of water at the bed, or the volume fraction of water in these areas, I should say. And I don't know I do know the average effective stress. But effectively, I have to just take this as a parameter. It shows up as a ratio. I have to assume something. I have to defend it. I don't actually know it, so it's not definitive. But I can calculate what the transmissivity would need to be for this case, and I get this map up here. It's in log units. I'm sure that you're not all used to thinking about transmissivities and whether these units make sense or not. So here's a coefficient of permeability for glacial tills by this author in the helpful unit of gallons per day per square foot. I can't remember how many data points are on here, but this is all from tills in northern US states. And just taking the median value and converting that into a hydraulic conductivity in meters per second, the transmissivity is just the hydraulic conductivity times the thickness of till. Median value is 10 to the minus 7. If we had a meter of till underneath the ice, then this value would translate right to this value. And the important point is just that tills, even as famously difficult as water transmission between till particles is, because they're a jumbled mess, they're still very squishy in comparison to what we would need them to be to keep the ice and the water pressure the same in these regions. Okay, now you might think that just drilling holes would be the way to go about things. This is a compilation of borehole data, where remember that in a borehole you don't know what the normal stress in the ice is, but you can say what the average is over some distance. You can measure the water pressure. These are all different holes, just 140 holes, 139 holes, drilled to the bed in Antarctica and Greenland and wherever else Colin could find data. And the point is just that the median of those data points is about 140 kilopascals. There's lots of scatter, and this is the kind of scatter that one gets on a diurnal basis, plotted as a function of ice thickness, if you like, on this side. So there's a lot of variation. But If the ice pressure and the water pressure were being balanced all the time, then we would expect that the normal stress on the ice would be equal to the weight of the ice, and it would have a component that's opposing motion. It's like the shear stress in the ice. And the average one would expect, sticking in this value here for rho I GH, would turn out to be about the average of N would be about the average of the driving stress. If, on the other hand, we thought that the effective stress was non-zero and that the shear stress was something like a friction coefficient times the effective stress, then we would expect the average to be more like twice as big, because friction coefficients are typically about a half. So it's, again, really a shaky argument, but you could say that our average shear stress is kind of on the order of 70 kilopascals we saw earlier, and doing some statistics, you find that N bar is different from 70 kilopascals by a lot. But it's not very different from what you would expect with a friction coefficient. So, another little piece of data. I think the best data, though, that suggests that the effective stress underneath glaciers is non-zero comes from geology. These are different images from underneath glaciers. This is in a tunnel in Svalbard, another tunnel in Svalbard, and this is a glacier in northern Canada, showing again a nice big thick bunch of sediment. And then this is from my backyard, where I grew up. This is just some granite that has been polished by the Cordilleran ice sheet during the last glacial maximum. Basically, when you see striations in rock that are driven by glacier transport, it's suggesting that there is actually interaction between the rock particles that the ice has picked up and the rock underneath. Okay? All right, so I have just a little bit of time left, I think. So I wanted to say that if we accept that the effective stress underneath glaciers, that they're not completely lifted up by water, which you probably never thought that they were in the first place, but turns out that glaciologists have, I want to talk about how the ice interacts with its bed. So the first mechanism is just going to be through developing a frozen fringe. So we saw the regime diagram before. This is the same plot of fringe thickness as a function of effective stress. If the effective stress underneath the glacier exceeds the level that's required to sink into the bed, which just depends upon the pore size, then we expect that we are going to do such a thing. We'll have the ice sink into the bed. But everything is heterogeneous. The water pressure is varying all over the place. The grain sizes are varying all over the place. We should expect that ice will sink in some places and not sink in other places. And we could come up with a rheology of this ice bed interface by thinking about if it sinks in some places and is able to develop a little shear fault by pushing the unsunk in places along, then that would be like plowing. On the other hand, it could have to actually deform over bigger bumps. And if we work out what kind of a basal resistance we would expect from that as a function of velocity, it would have a curve very much like the experimental curves for the far simpler cases with that we saw earlier. We've made an argument that this could explain why it is that our distribution of basal shear stresses is so narrow, that this median stress is only less than an atmosphere, that this would be consistent. Back to the laboratory. Well, this is ice sliding in the laboratory over glass beads. And you can see that we're developing a frozen fringe underneath here. So we're trying to do a better job. The laboratory apparatus is complicated. It's all put inside basically a meat freezer to keep the temperature constant, but then additional circulating bath around the outside and various other bells and whistles. But it's just a radial apparatus, and you're just seeing a cross-section view of that interface. And yeah, so you're looking at the side of this sliding ice. The bed, the till here are these glass beads. There's some bubbles. And the glass beads have been picked up to develop a frozen fringe that's that thick. There's a little bit of deformation in a shear band underneath the frozen fringe. That is not known, in a sense. It's got to be mostly unfrozen. Now, it turns out when you excavate this material after an experiment, often there are little mushy bits that are left behind down here, which could be broken off fringe. But it's difficult. It takes some time to actually lift this material out, and there's some uncertainty about what exactly you're looking at. Yeah. This here. This is ice that is infiltrated into the glass beads and picked it up, and this is not, the glass bead here and there, they're not moving relative to each other. They're essentially moving at the same speed as the ice. There is some frictional dissipation, but if I go back here, essentially there's some melting that is taking place at the bottom of the ice. But we still have a steady fringe. So it does affect, the friction at the bed does affect the heat transport. It is an important source. But it's not, doesn't change the dynamics in a... Yeah, and we do have that. I just don't happen to have that data with me at the moment. But yes, the way that this experiment was started off was just with pure ice up here, just a bed of beads down here, and this is a couple of weeks later how it has developed. And I can't remember the duration, how much this has been sped up, but it's some time period. Yeah. The beads start out saturated. It's starting out saturated with water, with deionized water. Yeah. So it's starting off wet porous medium, ice on top, start it going. After applying a normal stress with a ram, allowing water to drain out through the bottom and measuring the water pressure as well so that we can calculate the effective stress. But in this experiment, it's meant to be as simple as possible, yeah. To produce the ice in the first place? The ice is laid down in thin sheets. Actually, they start off with some ice chips, small sieved ice chips to try to make it a random fabric as the ice crystals grow. We want to keep bubbles out, so we want to freeze slowly from below. Yeah, that's basically it. Okay, well, so here's honesty. So this is after a different experiment. We've developed about a centimeter of till. Our model predicted this ice thickness or fringe thickness through time. This was the data. My collaborator tells me that actually this curve should be down here because the O-ring was leaking in some way and the effective stress that they thought they had was not the right. So this is the first effort, and by the time this makes its way to hopefully to publication at some stage, it will be much better. But it's that sort of behavior. The nice thing is we grew the fringe, okay? So that can make ice dirty, okay? This was something we didn't expect. So what they've done here is after an experiment with some other particles, They flipped the ice ring over top, so we're looking at the bottom, what used to be the shear surface. And somebody that asked earlier about, or I had mentioned that there were sort of clumpy bits left behind. You can see that this modeled surface, which was the sliding surface, the fringe is not uniform. This is what we would say is the fringe. There's this top centimeter or so. There's blown up right here. But all the rest of this ice is just filthy as well, just interlaid with all kinds of dirt. And looking under cross polarizers, you can look at grain boundaries, and you can see that the dirt is localized along grain boundaries. And in terms of the data, sectioning this stuff off, this is roughly the thickness of the frozen fringe here. And as you get up above the sliding surface, there's still sort of, several percent of debris content left in that material. And it's a little bit spotty and so forth, but this, I guess, must have been the Luss experiment. A different experiment using a different substrate, there's our fringe, and there's basically nothing up there. So sometimes dirt manages to find its way into the ice for this material. For this material, it didn't. Okay, so can we understand that? That's another way of getting ice up there. And that brings me to some beautiful work that Nye initiated, but his student Heidi Mader did, looking at the internal structure of ice, polycrystalline ice. This is meant to be an ice grain here, and there's another one on top and one to each side. And so it's highly idealized. But these little tubules on the boundaries are called veins. They connect at nodes. And again, this is an optical photograph for Heidi Mader's thesis work. And the Gibbs-Thompson effect is responsible for that water being there, in part, because the liquid pressure inside this vein is different from the ice pressure itself because of surface energy, as shown. Now, in detail, the Clapeyron equation, we need to add in solute. So this is the liquidus slope that Gray just talked to you about. So the melting temperature is affected by curvature. There's the little bit that comes from the difference between the densities, and there's the solute. We can take that phase behavior, we can calculate a suitably normalized to obscure the physics porosity, or liquid fraction. We can write down Darcy's law, and when you do that, you find that Darcy's law, and I've normalized this Darcy velocity by this liquid fraction, because the important thing is that Darcy's transport rate is a rate of transport over an entire cross-section. And what we're interested in is what is the water speed through each of these tubules on average, rather than what is the water speed through the entire space on average. Okay? And doesn't really matter about the details, but it turns out that there's a temperature gradient term and there's a concentration gradient term that make up the hydrodynamic pressure gradient that drives flow. And temperature and concentration have to evolve according to the same equations that Gray has been taking you through in a much clearer fashion. But we can make a model. We can solve these equations and see what these velocities are, and can we drag particles up into the ice with this mechanism? And the answer is, maybe. So this is just an illustrative calculation just to show you one thing. What we've got is a picture of a glacier bed here, and we have to think about, well, what kind of perturbations do we expect to have at a glacier bed? We expect to go from places where we have pre-melting to places where we're over top of cavities. And that gives us a sort of a scale of how much of a temperature variation do we expect to take place at the bed. And we want to use that temperature variation to drive our transport. And the point I wanted to make is just that this curve, which is the salt curve, and this curve, which is the ice curve, look like mirror images of each other. And you can see that the Darcy transport rate depends on both of these gradients, but they're going in the opposite directions. So the fluxes wind up being extremely tiny, and not much water makes its way up into the ice. So difficult to drag particles up with this mechanism. This is the flow rate, average flow rate in the vein, sort of at 10 to the minus 6 millimeters per second. You can't really drag a particle much with that. However, that's not how our experiment worked. What we did in the experiment, or what Dougal and Luke did in the experiment, is they've got to couple this drive to the ice. And so how they do that is they essentially make it cold on the top as they press this drive in, and then they lower the whole thing into a better configuration where they can bring it up to the melting temperature. So they want to be operating with the ice always close to its melting temperature, but they got to get this thing stuck into the ice to begin with. And so there's a thermal perturbation at the beginning that has to relax, and as a result, it turns out that you can get maybe, a healthy fraction of a millimeter per second, which suggests that you can entrain micron-sized particles. They're maybe a factor of 5 smaller than what we see, but given the simplicity of the model and the messiness of the world, we feel pretty good about it. So you can get a few particles up into the ice that way. We see particles in the ice. There's yet a third mechanism, which is the last mechanism I wanted to mention, and I think is the important one for describing processes like that led to these kinds of dirt bands, and possibly the dirt bands that you saw in my opening slide. And that, again, involves the fact that you're sliding from regions that are in close contact to regions that are cavities, and so that the water pressure and the ice pressure have to be equal in those regions. And the melting temperature changes as we go from the pre-melted regions to the drained regions, to these regions here. And it increases, importantly. So here, this is the equilibrium temperature. Here, schematically, it's a little bit higher. So that means that there's heat transport. It's going upwards. And we freeze on a little bit of material. And by the time we get to the other end of this cavity, we have some thickness here. And then the temperature gradients reverse, and we're going to melt this material off. However, because some of that heat has been transported upwards, and because the diffusion equation is, after all, not reversible, this process of freezing on and melting off is not reversible either. There's a lag. So there's not symmetry between the freeze on and the melt off. And you predict that there will be net freeze on as a result of this process, just as long as there's more of the bed is covered by close contact regions than is covered by cavities. Okay. Numerically, how does this all work? It turns out it's a pretty simple balance to solve. You can solve the heat equation to calculate the temperature distribution and ask yourself how much ice is going to freeze on over the time that you're sliding over a pocket of ice. And helpfully, that thickness depends inversely on the Stefan number, which is right here. And it depends upon the Peclet number as well. That's the square root of it, I suppose. But when you stick this into a model, you predict that the thickness for sliding over a single cavity is in the range of 1/10 of a millimeter to 10 millimeters for typical sorts of conditions. If you imagine that you're sliding over a sequence of cavities, you can also solve that problem quite easily. And this is that plotted up for different fractions of cavity spacing. And after sliding 100 kilometers in Greenland at an effective stress of 10 kilopascals, which is a reasonable number with this much water at the bed, you get 10 centimeters of net freeze on. So the idea is that we'd be laminating tiny little layers of new ice in this way, and that sometimes they're going to incorporate little bits of dirt while they do that. Okay, and to convince you that this is possible, perhaps, this is a picture from Antarctica. It's a movie. It looks like things are going back by you in this direction. Actually, what they're doing is lowering a camera into the Cam ice stream, or the Willans ice stream, I should say. And we're seeing all these little bits of dirt off in the side of the ice above the bed, heading down towards the bottom, which is coming in a few tens of meters. This is in a cavity in Svalbard, in a glacier there. Again, these nice fine little layers. And it's just another way that ice and dirt can interact with each other, aside from frost heave and frozen fringe formation. And I think I'm going to leave it at that. We're done with subglacial stuff. We've talked about frost heave. Tomorrow, I want to spend a little bit of time on this, assuming that I can get my slides together. And as always, there's the references.